In the last video, we studied how to apply the NPV model to determine whether a project is worth of investment or not. In that video, I briefly mentioned that we not only need to consider whether the NPV is positive or not. Sometimes we also need to consider the relative value, right, between the positive NPV and the initial investment. If you are getting very, very small profit, but that requires a big investment, it's probably not a good project, right? So we need to consider the return, so not only just the positive, right? So before we only require NPV to be positive, then we say the project is worth investing. This is our conclusion, right? This is still correct, but sometimes we wonder more. We ask more, right? So let's say what would be the corresponding return of taking this project, right? We need a different measure, right? So that's why we need to introduce a new concept, which is called internal rate of return, and in the future we simply call it IRR. It is the interest rate that equates the PV of cash inflow with the PV of cash outflow. Right. So in other words, IRR is the rate such that NPV equals 0. Okay. So here what we do is we solve an equation. Right. We know the definition of NPV. We establish an equation and we try to solve this equation to get IRR, because IRR is a rate. The good thing of rate is it has no unit. Then you have a good idea of whether you should invest in it, right? This is better than NPVs because NPV is a number with unit, right? It's in dollars or in euros, right? And it does not give us the full information, right? For instance, let me give you an example to think about. Invest, let's say 1 million. This leaves you to an NPV equals 2. Okay. This is case 1. Case 2. Invest 500K, and that gives you an NPV equals, let's say, $8,000. Right. So both give positive NPV, means both are attractive. According to our previous conclusion, we should invest in both projects if you have $1.5 million. If you don't, let's say you only have 1 million, right? Then you can take project 1, or you can take project 2, but still leave 500K, to be spent somewhere else. And then my question is, which one is more attractive, right? Project 1 or project 2, right? So if you just use NPV, it's somehow difficult to get an idea, because here for project 1, you do get more NPV, higher NPV, but you need to invest twice of project 2, right? So if it is possible to do project 2 twice, then it actually gets you more money, right? So if you can double project 2, you will get actually 16,000, right? That's a lot more than 10,000. But usually that is not the case. Then you will need to think about, what am I going to do with the remaining 500K? If I can find some other place to invest and make more than $2,000, then I should take project 2 along with that thing, right? Otherwise, I should go with project 1. But anyway, the main purpose of using this example is to demonstrate that sometimes number itself, absolute number itself may not be good enough, right? We want relative number, we want return, right? We want percentage. That tells me, that gives me more information. That's why we want to calculate IRR, because IRR is actually the internal return of the project. Okay, internal rate of return, not internal rate of rate. Okay, but the question is, it's often very difficult to calculate this number because it requires solving a nonlinear equation. Let's continue that house example. If you recall, now let's say we don't know the interest rate, because previously what we assume, in this example we assume interest rate is 8%. Okay, that is the interest rate or the cost of capital. Now we don't make that assumption. We assume there exists a rate such that NPV is 0. So we try to solve this. Okay, this is the future income. So let's discount. This should be equal to the present value of cash outflow, right? Okay, we are trying to solve for this equation. So let's say J is something we are trying to solve. Okay, so if we use J, remember J is the monthly interest rate. Okay, and obviously 1 plus J raised to the power of 12 would be 1 plus I. So we use discount. We discount, so that is V. Okay, so that is how we get V. So V equals this. So now this is the equation about J, but it is in a highly nonlinear term. So so let me rewrite it. So we would have, let's plug in the standard formula. Okay, this is not easy to solve, right? It's rather complicated, and your financial calculator can actually solve this type of question. But in general, this is a nonlinear equation, and it's likely that you wouldn't be able to find a solution directly by hands. One thing you can do is by trial and error. So for instance, you can just try. So let's say you try J, you try I is, so you can try I is 15%. That means J is about 1.1715, and then you get NPV is negative something. Okay, it's negative. Then I will need to try a less number. I try a less interest rate, and then I will get NPV is about 125. Okay, then I get a positive number. Then my IRR must be something between, right? Must be between 14% and 15%, because in most cases this is a monotone function, is either increasing or decreasing. In this case, it's decreasing. So when interest rate goes down, the value goes up. Right? When you check this, when interest rate goes down, the value goes up. Right? So you can do trial and error, and then you can do 14.5%. You know, it goes all the way to the more actual number. But anyway, if you have some software, you can get the actual number of J. Once you get J, you can get I, right, by this formula. So 1 plus J to the 12th minus 1, that is our annual interest rate. Okay, I should also mention that when we quote IRR, by convention, we quote IRR in annual effective rate. Okay, so it's the corresponding I for the project. Okay, so in this case, it's about 14%. It's a little bit above 14%. Okay, remember previously what is the number? We set R to be 8%. Now it's very easy to do the comparison. Since my IRR is 14.1648%, which is greater than the cost of capital, we should take this project. Right? So from the end of this example, I'm sure you can understand why we introduce IRR and why IRR is important, and it's a very easy, effective measurement, right? All we need to do is to compare the IRR of a project to the cost of capital available to us, the best one available to us, because we can invest all our money in something we already know at the return of 8%. We earn 8% from there. But if this project gives us 14%, we should go with this new project, right? It's very easy to make a decision once we know IRR. So that's everything behind IRR. The textbook actually gives you a graph of IRR. That is actually very easy to do. I'm sure you will need to learn a software, right? Either R, Python, MATLAB, anything, Maple, Mathematica, anything can do it. I mean, Excel can do it as well. So this is a rather easy programming or software technique to draw the picture. I leave that to you. The textbook does show it. It has a little like a decreasing curve. What you do is you draw this is your NPV. This is your interest rate, R, not exactly R, it's what you try. So this is the rate, right? It's decreasing, and at some point you will get 0. This is the point that gives you IRR. Okay, you can draw a graph like that. Let's use an example to illustrate a little bit more information. That is example 5.2. A bank lends Diana $8,000 now. She repays $600 at the end of each quarter for 5 years. Found the annual effective internal rate of return. So we just equate. On the left-hand side is just 8,000. On the right-hand side, I'm supposed to calculate the present value. So there are two notations. The first, I write the notation. I always use the notation I prefer. I don't like the extra notation. So there are 4 quarters each year for 5 years. There are 20 quarters. That is the notation I usually use because it only uses the most standard annuity immediate. But if you want, you can also calculate the annual payment, which would be 4 times 600. And because this is a piecely annuity and P is 4, so we can use this. But here it will be the number of years, 5. This J must be the effective interest rate for the corresponding time unit. In this case, is quarter. So from here, we can write down the equation. So of course, you also have formula from there if you want to apply that, that's also okay. So from here we should be able to get j, right? So once we get j, I would be 1 plus j to the fourth minus 1, right? That would give us IRR. So you should you can try, but let me give you some of the trials. Okay, so let's try I with 16%. Okay, and then what you would get? You would get you actually need to divide this over to get the result. So let me follow what the textbook writes. So after a little work, what you can get would be 13.33. So actually this goes on forever. 1 minus 1 plus I to -5. Okay, and instead of dividing by j, I would divide by 1 plus I to the quarter minus 1. By the way, this is j. Okay, so in here, I know this is once I goes up, the value would go down. So I try I 16%. Then I get my right-hand side would be 13.86, which is greater than my left-hand side. Okay, so it's bigger. So I will need to take it down. In order to take the right-hand side down, I will need to increase the interest rate to 17%. Then I recalculate. It is 13.59, which is still greater than my left-hand side, right? I will have to go further, 18%. So my new right-hand side now becomes 13.32, which is a little shy of my left-hand side, okay? So I would know for sure my actual I would be somewhere between, right? So it would be somewhere between. How can we get the result if I already know those two? If I already know those results. So then we apply what is known as the linear interpolation. Okay, then I need to put a weight for this, okay? Because usually what we do is to give you a little idea. So the graphs may be non-linear, but what I do is I assume it's a linear graph. Okay, so this is what I want, 13.33. Okay, so here I try 17%. I get a value which is 13.59. Okay, then I try another value, 18%, which is 13.32. Okay, now I apply a linear function to approximate this value. That means it would be the weight between those two. Right? So you just need to figure out what is this weight, what is this weight. Right? By linear interpolation, we easily know this would be, so first of all, would be the total distance between those two numbers. Okay, for 18 is here, so it's close, right? So we should actually use this guy minus what you want. Okay, the other side is okay. That's because even by looking at this graph, we know the true point is very close to 18. So that's why the weight is actually bigger for 18 than for 17. So in the end, I get the number is 17.96. this is when you don't have actual software to get the number. I expect all of you to understand this, because for the exam, usually I give you a range, right? So it's between 17 and 18. So it's possible that you may not get the exact answer, but it's relatively easy to get a range. It's between something and something, right? So here we can even apply the so-called linear interpolation to get a very, very good estimate. This is a good estimate, okay? We actually have more examples, but for example 5.3, I leave that to you because it's pretty much the same, and it's just you will need to solve another linear equation, okay? So now we need to discuss a little bit more, okay? In a typical investment project, what you need to invest is upfront, right? Let's say you buy a property first, right? You pay first, and then you receive some cash inflows in the future. So that comes the question, right? You pay, when you pay, everything is certain. You know how much you need to buy, you need to pay when you want to buy a property, but the cash inflow is in the future, right? Even when you think this is a good project, you invest now, what you will receive is something uncertain, right? So what you have is you have a mixture of cash flows, right? You will have some outflows, maybe in earlier stage, and then you start to get cash inflows in much later stage. So I think that is a good reason why IRR is important. But when you think of IRR is a single rate, right? So it does not really exist. It's more or less an imaginary rate that helps us to do the comparison, to analyze a project. But in reality, there are many factors you need to consider, right? So what I just want to mention is, in real life, interest rates change, right? So let me type here. So IRR is a constant rate, which we imagine once applied leads to a zero NPV. Okay, the key word is here. It's okay. It's a constant rate. Okay. So now the question is, what if the actual interest rate? What if the actual interest rate or cost of capital is changing? Right? Let's say right now the cost of capital is probably low, right? Because the interest rate is low, it's close to zero. But maybe in a few years, the interest rate will go back to its relatively normal stage, right? Then what would you do, right? Let's say you are looking at a project that just spans 20 years, right? There's no way that the interest rate will be still zero, 10 years from now, right? So at least let's hope that's not the case. Then how do we analyze everything? So now we know the cost of capital is actually changing, but when we apply the concept of IRR as a constant rate, right? So that gives a little a mismatch. So the textbook actually have an example. Let's briefly study it. Okay. We will probably come back to this later on. But again, I'd like you to actually think about this basic question, right? Maybe we will not tackle this problem in this course because it's a rather complex question. But at least know the possible drawbacks of IRR, right? It's a constant rate, and it's often the case that the underlying interest rate is actually changing. So Vanessa invests $5,000 at the end of next 15 years. And her investment earns an interest rate at an annual rate of 10%. The interest that she receives at the end of each year, so this is per year, is reinvested and earns at an annual effective rate of 5%. So interest is reinvested at 5%. So I believe we solved one of this type of questions before. Calculate the accumulated amount of total investment at time 15 years. Okay. So here it's what you have is two different things, or two different interest rates. The first one is how you get interest rate, how you get interest, how you accumulate interest. But this is different from our traditional standard example in the sense that interest is reinvested at a different rate. Right? We often assume the interest is reinvested at the same account, earning the same interest rate. Then at the end of 15 years, if it is the same, then by the end of 15 years, we would have 5,000 times 1 plus R or 1 plus I to 15, right? That is the easy case, but obviously this is not the case for this example because 10% does not apply to your interest. So now we need to analyze, okay? I believe we did one of this before, so now let's do it again. Okay, so she invests money for different purposes. For here, what we have is so assume here she invests $5,000 at the end of each year. So this is the first time she invests. So at time 1, there's no interest. So let's say we put interest underneath the line, right? Because the first deposit is made at the end of year 1. So it accumulates nothing, right? So over the first year, she actually doesn't invest. So the interest rate, the interest is 0. Okay. In the second year, since there is 5,000 at the beginning, that will accumulate interest, right, at 5%. So it would be not 10%, not 5%, excuse me. So that means at the end of year 2, she would get 500 as interest. This is the interest. Okay. Next, she deposits another one. So it's somehow difficult to write. So let me put two things down here. So what I do is there are two numbers. The first one is the amount she deposits, okay, at that time, and there's another amount that is the total principal. So in the at the end of year 1, both of them are 5,000, right? Because that is her first deposit. In the second year, she will deposit another 5,000. So at this time, her total account would be 10K, right? So at the end of 3, how much would be? It would be 1,000, because you would apply 10,000 times 10%, right? That would give you $10,000 interest, right? So this is the interest from there. Okay, then she deposits another 5K. Now the total becomes 15K. So meaning this will be 1,500. Okay. So and so on, right? So each time she adds new 5K. So here would be 20K, etc. Right? Up to the last one. So in the end, we know here right? So what would be the total amount in her principal account? At the end of each year, she invests 5K for 15 years. So in the end, she will have 75K by the end of 15 years. Okay. Now, that is only one part of the question, right? Then we need to study how about the interest part, right? We haven't analyzed the interest yet. We only analyzed the value at the corresponding point, but we want everything to be calculated at the end of year 15. So for this, it becomes 500 times 1.05. So I need to use 5% because 5% is the rate for interest for how many years? I have 15 years in total, right? From 0 to 2, there are 2 years, meaning from 2 to 15, they are 13 years. Okay, so that is the first interest. Now I study the second one. Is 1,000, right? Okay, what would be the trend? 1,500 times 1.05. This is 11, right? So you can easily see the trend, right? So this is the 500 times 1. So let me write this. Let me write this as 500 times 2, 500 times 3. What do you find in common? I write this as 500 times 1. 1 plus 13 is 14. 2 plus 12 is 14. 3 plus 11 is 14. So the next one times 4, this is 10, right? Goes on until the last one must be 0, right? 0 plus 14 is 14. So what would be the total? So it's actually the accumulated value. So 75,000 is the principal, total principal. There are 5,000 deposits. Then I need to calculate this whole thing, right? So we can fact this out. Then it becomes 1 times this, 1, 2, 3. So this is an increasing annuity, right? For how many years? 14. What is the interest rate? 5%, right? So you can easily calculate. So here, this example, it's still, naive because we know there are just the 2 interest rates, one for the principal to get interest. The other one is for the interest to accumulate further interest. They are different. So that's the end for the first section.